Section 1.3 is dealing with frequency, frequency tables, and levels of measurement. Before we get into this, just some information about rounding and accuracy of answers and things. So a simple way to round off your answers as accurately as possible is to carry your final answer one more decimal place than was present in the original data. So if your original data had one decimal place in all of its information, then you're going to give your answer with two decimal places. And as much as possible, we want to round off only the final answer. Don't round any of the intermediate results. Again, if possible, sometimes we get results that are super long, and to write out all those decimals is impossible. So if it does become necessary to round off your intermediate results, carry them to at least twice as many decimals as your final answer. So again, if your original data has one decimal place and your final answer is then going to have two decimal places, if you've got to round off stuff in the middle, then you're going to want to keep four decimal places. And that's going to be important as you start giving numerical and statistical answers in MyOpenMath, that you have that rounded off correctly so that you're going to have an accurate enough answer. So the goal is that we keep our answers as accurate as possible. So don't round them unless you have to, but if you have to, keep twice as many decimal places as your final answer is going to need. Now, having talked about the accuracy of our answers, we want to talk about different levels of measurement. So when we talk about variables, these variables are going to be at different levels of measurement based on what we know. So the first type is a variable is at the nominal level of measurement if the values of the variable name, label, or categorize that variable. So things like colors, things like styles of vehicle, things like even you could last names, nationalities, different things, states that you live in. These would all be nominal levels of measurement. In addition, the naming scheme does not allow for the values of the variable to be arranged in a ranked or a specific order. So there's no like intrinsic ordering that would go with it. We're going to see some examples later on where they do have names and there is an order that's automatically assumed. But when you think about colors, for instance, you might have blue, red, green, and yellow. There's no this one's better than that one, or this one's a higher ranking than that one. They're just colors, and you just have them. So there's no ranking in the nominal level of measurement. The variable is at the ordinal level of measurement if it has the properties of the previous level, the nominal level of measurement, and this time the naming scheme does allow for the values of the variable to be arranged in a ranked or a specific order. So this time the values can be arranged. So that's the difference between nominal and ordinal. Ordinal, like thinking order. Nominal, if you think back to that root word, it's name. So the first one you can name it, the second one you can name it and order it. The third level that we're going to deal with is the interval level of measurement. And this is where we typically get into numbers more often. And here's what we've got here. Interval level of measurement. The variable is at that interval level if it has the properties of the ordinal level of measurement, which means it can be named and it can be ranked, or it can be grouped and it can be ranked. And the differences in the values of the variable have meaning. A value of 0 in the interval level of measurement does not mean the absence of a quantity. So this is the key here. Does not mean the absence of a quantity. So just because you have a 0 doesn't mean there is none of something. Let's see if I can think of an example that doesn't give away our future examples. Well, I can't think of it right now, but recently we had a cold streak, so we had some temperatures that were 0. But then we had temperatures that were below zero. And when you measure temperature, you are measuring heat. And a temperature of zero does not mean that there is no heat. It just means the heat is, there's not enough heat for us to be happy about it. So in the interval level, you've got these numbers, you've got your arithmetic that you can do, adding and subtracting. You know, if you subtract 70 degrees from 30 degrees, you know that that's a 40-degree difference, and it gives you an idea that one is bigger than the other and how much different they are. But again, the key here is that zero does not mean, a measurement of zero does not mean that there is none of something. So to finish this up, arithmetic operations such as addition and subtraction can be performed on these values, and they actually give you some meaningful results. A variable is at the ratio level of measurement, and this is the highest level, the ratio level of measurement, if it has the properties of the interval level of measurement and the ratios of the values of the variable have meaning. A value of zero in the ratio level of measurement means the absence of a quantity. So that's, again, that's the key. If you've got a zero and it means the absence of a quantity, that means you're dealing with the ratio level. Arithmetic operations such as multiplication and division can be performed on these values of the variable. And the reason for that is because of the fact that zero means that there's none of it. So an example here would be like your bank account. If you have zero in your bank account, it means you have an absence of money. You don't have any money. And so, like for instance, if I said that I have, let's just say $100 and somebody else has $200, they have twice as much money as me. On the other hand, if we were dealing with temperature and I said, oh, well, the temperature was 50 degrees today, it's going to be 100 degrees tomorrow, that doesn't mean there's twice as much heat. So that's kind of the key there in the ratio level. These ratios have meaning. Okay, but again, it's going to be numbers, but this time zero means the absence of a quantity. Example 116, a study was conducted to assess school eating patterns in high schools in the United States. The study analyzed the impact of vending machines and school policies on student food consumption. A total of 1,088 students in 20 schools were surveyed. Determine the level of measurement of the following variables considered in the study. So is this going to be nominal, ordinal, interval, or ratio? The temperature of a cup of hot chocolate every 15 minutes until it reaches room temperature. So let's say if you think about it, that cup of hot chocolate might start out at, I don't know how hot it would be, maybe 110 degrees. And then it goes down to 100 degrees, so it decreases by 10 degrees. It goes down even further and eventually gets down to room temperature, which would be around 70. So is that level of measurement, or what is that level of measurement? Well, we can see its numbers, and we can see that subtraction makes sense. It went down 10 degrees and down further and down further. That's subtraction. But as I mentioned, a temperature of zero does not mean the absence of heat. So this, and again, I gave it away when we were talking about it, but this is going to be the interval level of measurement for this first one. For B, whether or not the school has a closed campus policy during lunch. Well, the two options there would be it has an open campus or it has a closed campus. So they can definitely be labeled. But open or closed, there's no better or worse there. So that's just naming the information, and that is going to be the nominal level of measurement. Letter C, class rank. So your class rank or your class grade, your freshman, sophomore, junior, or senior. This is naming the data, but also notice there is an implicit order to them. Freshman means 9th grade. Sophomore means 10th grade, junior means 11th grade, senior means 12th grade. So this one, you're getting not just the label, but you're also getting an order or a ranking, and that is the ordinal level of measurement. And letter D, the number of days per week a student eats at school, eats the school lunch. Well, you're counting the number of days. So to go back to some of our previous topics, that's a count. So that's going to be quantitative and it's going to be discrete. But notice 0 days per week means they ate not at all. And so that's going to be your ratio level of measurement because, again, it's numbers. The arithmetic has meaning, but also 0 means none. So that's the ratio level for that one. Data that is not organized is referred to as raw data. So before it's been organized, you just collect it and you put it in a big list. That is raw data. In order to start organizing it, one thing that we can do is we can make a frequency distribution. And this lists each category of data and the number of occurrences for each category of data. The frequencies are the counts of those occurrences for each category. So looking at that, we can also have a cumulative frequency. This is the accumulation, or where you add up all of the previous frequencies with the one that you're looking at. And we're going to do an example of this so you can see how each of these work. We also have a relative frequency. And a relative frequency is the ratio, which can be written as a fraction, proportion, or even a percentage of the number of times a value of the data occurs in the set of all the outcomes compared to the total number of outcomes. So it's going to be a fraction or a ratio of that category compared to all of them. And then finally, we also have a cumulative relative frequency, and this is the accumulation of the previous relative frequency. So you're going to add all of them up that are less than the one that you're dealing with at the time. So let's do an example of this. It says the following data represents the number of available cars in a household based on a random sample of 20 households. So if you notice, you look through our list here, our outputs, our number of cars are going to be 0, 1, 2, 3, and 4. Then if we look at the frequencies, we're just counting how many times something occurs. So notice we've got 1, 2, 3 zeros. We have 1, 2, 3, 4, 5, 5 ones. We have, let's see, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9 twos. So this is our frequency distribution part. We're just writing down how many times each option occurs. Notice there's only 1 3, and then we've got 2 4s. So if we add those all up, we should get 20. So 3 plus 5 is 8, 17, 18, 20. So that's good. This would be, if all we were doing was a frequency distribution, these first 2 columns right here, that would be what that would look like. But if we go on and we put another column on there and we're going to do the cumulative frequency, I'm going to do that one in green. So the cumulative frequency of 0 means how many outcomes were 0 cars or less. So in this case, that's just 3 that had 0 cars. When we go to cumulative frequency and we go up to 1, it means 1 car or less. So we'd have the 5 plus the 3, so that's going to be 8. When we go to 2 cars, that means for cumulative frequency, 2 cars or less. So that means we're going to have the 9 plus the 8 from the previous groups, and that's going to be 17. When we go to 3, that means 3 cars or less, so it's going to be the 1 plus the 17 from the previous groups, and that's going to be 18. And then for this last one, when you get to the highest group, you're always going to have everything. It's the 2 plus the 18 from the previous groups. And so that is your cumulative frequency. Now, when we go to relative frequency, that's where we're starting to get division involved. So that's where this statement, use 2 decimal places when rounding if necessary. And so our relative frequency is going to be each individual frequency divided by the total. And there are a total of 20 households that were viewed here. So for the first one, it's going to be 3 over 20. And if we make that a decimal, it's 0.15. So either 3/20ths or 0.15 as a decimal. If we go to the second one, that is 5 over 20. Now, if you're going to leave it as a fraction, you need to reduce it. So that would be 1/4, and that would be 0.25. So if you're going to leave it as a fraction, always reduce it, or you could just change it to a decimal. When we go to the third one, it's going to be, and just as a reminder, it's this one compared to the total. So it's going to be 9/20, and that would be 0.45. And then we go to the next one, and it's going to be 1/20, which is 0.05. And then finally, the last one is going to be 2/20. And if we reduce that, it's 1/10. And that's going to be 0.1. So those would be our relative frequencies. And then to finish this up, we've got our cumulative relative frequency. And that's where we add up or accumulate all of the relative frequencies. So the first one still is going to be, I'm just going to do the decimal, 0.15. For the second one, one car, the relative frequency was 0.25 plus the previous one. So 0.25 plus 0.15 is 0.4. So that's adding this one and this one together. When we get to two cars, it's two cars or less. So it's going to be the 0.45 plus the previous one. So that's going to be 0.85. And then again, that's the first three categories. When we get to the next one, you've got the 0.05 plus the previous categories. It's going to give you 0.9. And then finally, when you take that 0.9 and add the 0.1, you're going to get 1. You're up to all of them are at that level or less. So again, you are not usually going to be asked to do all 4 of those at the same time. You might have just a frequency distribution. You might have just a cumulative frequency table. You might have a relative frequency, or you might have a cumulative relative frequency, or maybe combinations of some of those. You just have to look at what they're asking you to do, but that's the process you would use every time, regardless of which ones you were using. You just pick the correct row and you do it that way. Now, sometimes we're dealing with situations where we have very large data sets and it doesn't make sense to try and list every individual outcome individually. So what we have here is what are called class intervals, and class intervals are used for organizing data, usually for data sets with a large range of values. In general, here's what we know about class intervals. They're going to usually have somewhere between 5 and 20 classes, depending on the number of data. Now in our class, we're going to keep it with like maybe 5 to 7. I'm not going to have you do up to 20 classes. That would be too much for us. If you were doing a big study and actually doing it for a job, you might have up to 20 classes possibly. The class intervals need to be equal in size, which means the differences between the consecutive lower limits will all need to be the same. We'll look at that. And they need to contain all the data in the set. So everything in the set, all the data needs to fit into exactly one of the classes. So for example, if the first interval happens to be 120 to 129, the next interval would have to start at 130 and go to 139. And that would mean the class width is 10, because the way you'd get that is by subtracting your lower limit here from your lower limit there. So the 130 minus the 120 tells you the class width is 10. And if you think about that, if you write out 120 to 129, there are 10 numbers there. So that's why we call that the class width. So the interval size is the same as all the other ones. So all of them would run from, the next one would be 140 to 149, 150 to 159, and so on. The class widths will all be the same, and the difference between the consecutive lower limits will always be 10. Now, when we want to figure out how large to make our class widths, here's what we do. We're going to start out by subtracting the smallest value in the set from the largest value of the set. This is called the range of the set. Then we take that range and we divide it by the number of class intervals that we want to have. And like I said, for us, that's going to be like 5, 6, or 7, somewhere in that range, somewhere in that group. This gives us the class width for each interval. So the class width, this is written out as like formula, the largest value minus the smallest value, and then divide by the number of class intervals. Now, the one thing we have to remember is, and capital letters here, this is emphasized, we always round the class widths up. So if you have class width and you divide it, it comes out to 3.2, you would round it up to 4. If it comes out to 4.8, you'd round it up to 5. And even if it comes out to 7, you'd round it up to 8. And the reason for that is if you don't round it up, you're not going to end up including all of the data values. So we always have to round it up no matter what. We will use the class midpoints for when we have to graph the quantitative data, and we can easily find those midpoints by taking the average of the lower and the upper class limits. So we're going to see that in a little bit as well. Example 118, the total cost of textbooks for the term was collected from 24 different students. Create a frequency table with 5 class intervals. This is also called a grouped frequency distribution table, and you will see this on the homework called a GFDT. So make sure you maybe underline that or highlight it in your notes so that you know that when you're looking at it. So looking at these, being the nice person I am, you can see that they are already in order. So the smallest value and the highest value, if we want to take the biggest value for the class width, the biggest value is 320 minus the smallest value, which is 140. And we're going to divide by, if you look back at those directions, I told you to do 5 class widths. So if we subtract that, we're going to get 180 divided by 5, which is 36. Now, very important. We need to take our class width and round it up to the next number. So we're actually going to make it 37. So the way we make our table, we are going to put our smallest value in here, 140. To figure out the next value, we're going to take that 140 and we're going to add 37. So 140 plus 37, and that's going to give us 177. And I'm going to grab my calculator here to do the rest of these. So 177 plus 37 again. 177 plus 37 gives us 214. 214 plus 37 gives us 251. And 251 plus 37 gives us 288. So by adding that 37, we have come up with all of the lower class limits. Now we want to find the upper class limits. So the upper class limit is always one less than the next lower class limit. So if I'm going to find this value, I look right here and I just put the previous number in, 176. So that means the next one's going to be 213. The next one's going to be 250, one less than the 251. Next one will be 287. Now the problem we have is we don't have something to just figure out this next one. But notice, since all of these, we added 37, added 37, added 37, the same thing happens here. So 176 plus 37 gave us the 213, plus 37 gave us the 250, plus 37 gave us the 287. So we're going to add 37 again to find that last upper class limit, and it ends up being 324. Now to find the midpoints. Midpoint. And I'm going to find the midpoint of that first class. We're going to take the two values and add them together, 140 plus 176, and then we divide by 2. We just take the average of those two boundary points. So 140 plus 176 is 316 divided by 2, and that gives us 158. So our midpoint here is 158. Now, again, we could do the midpoint of each of those by taking the average of each group, but we can also just add 37 because all the different groups are 37 apart. So 158 plus 37 gives us 195 for that next midpoint. Plus 37 again gives us 232. Plus 37 again gives us 269. And finally, adding 37 one more time gives us 306. All right, so now that we've got the classes figured out and the midpoints figured out, we're going to go ahead and find the frequency of each. So the first class runs from 140 up to 176. So that's going to be 140 up to 176, which is going to stop right there. And there are 4 items in that class. Next, we've got 177 to 213. So actually, that's just this one. So there's only one item. Actually, I just used the corresponding color that I used, I guess. Okay. The next one runs from 214 to 250. So it's going to go here, 214 to 250. So it goes up to there, and there are 4 of those. Next, we're going to go from 251 to 287. So it's going to start here and go through here up to here. So there are 5 of those. And finally, we're going to run from 288 to 324. So 288 to 324 is going to give us all the way to there. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 outcomes there. Wait, 1, 2, 3, 4, 5, 6, yeah, 10. So that's what our grouped frequency distribution table would look like. Now, one thing I want to mention, if we don't increase this to a 37, if we use 36, this would be 176. Don't do this, but I'm just showing you what would happen. This would be 212, this would be 248, and this would be 284. This one would end up being 175, 211, 247. This would be 283, and then this would be 319. Okay, if we added the 36. And you'll notice the problem that we have there is these 2 values would be left out of our grouped frequency distribution table. So that's why it's always important that you round that number up to the next number when you're finding that class width. That is the end of section 1.3. You've got those 9 problems to work on, so you can take a look at those. Again, if you have any questions, please make sure that you let me know and give me a call, or not give me a call, but send me an email, send me a message so that I can try and help you with those.